Genetic engineering laboratories are specially designed to perform experiments in the most efficient and optimal conditions. In order for a laboratory to manipulate equipment and materials, it is important for him to know their location and function. This will prevent possible accidents that may occur within the laboratory, preserve the calibration of the equipment, and to reduce human-machine mistakes. Methodology. Micropipettes are devices that allow a precise measurement and transference of volume in order of microliters. To guarantee a successful experiment, it is necessary to know how to use them. There are different sizes of micropipettes. For example, the P100 is used to make measurements between 100 and 1000 microliters. The P20 is useful when it's necessary to measure a volume between 2 and 20 microliters. The way in which a micropipette is adjusted is by moving the security lock and to move the plunger rod until the volumeter display shows the quantity that it is needed. Taking samples with micropipette. The first step is to identify the size of micropipette you need. This depends on the volume you have to measure. Choose the end that best fits the micropipette. It should not be loose or you will have incorrect measurement. To take a sample, push the piston to the first stop. Submerge the tip a few millimeters into your sample and slowly release the piston. Make sure you are not submerging the entire tip, neither touching the borders of your container, as it is contamination source that will go directly to your sample. To deposit your sample, just push the piston up to the second stop. This will release all the liquid inside the tip. Make sure to make this step slowly, so your sample will be gently deposited into your recipient. Always seek to take and deposit your samples with the micropipette in vertical position.
As this practice is an introduction to the genetic engineering laboratory and the manipulation of micropipettes, this first experiment consists in the measurement of samples of deionized water, with the values given in this table: 2, 10, and 20 microliters for the P20, 20, 100, and 200 for the P200, and finally 100, 500, and 1000 microliters for the P1000. First, it was necessary to take the corresponding pipette and adjust it to the indicated volume. Then, the sample of water is taken and placed in the analytical balance to determine its mass. Based on water's density, about 1 gram per milliliter is determined if the mass corresponds to the volume that was wanted to obtain. The experiment is repeated tenfold for each measure, and the data in grams is registered in the table. The experiment is repeated 5 times with the different volumes and micropipettes. With the P200, 3 samples of 48 microliters are considered, recovering a final volume of 144 microliters. And the P20 considers samples of 3.5 microliters to get 14 microliters back. With the objective of generate an accurate technique for micropipettes manipulation, in this experiment is necessary to make a lot of measurements. Using the P1000, the experiment consists in taking 330 microliters of water 3 times and collect it into a microtube. After that, the micropipette is adjusted to 990 microliters, waiting to retrieve the same volume back. This table shows the results obtained by doing the experiment number 1. The data within the table is given in grams. It was also calculated an average and the standard deviation. As here is shown, all the results are very similar to each other, and close to the prediction of water density of 1 gram over milliliter. A critical point in this analysis is the consideration of errors, like the fact that real density of water is not necessarily the one predicted before at the temperature in which the experiment took place, and that the weight of the sample of the P1000 was made with a non-analytical balance, creating a lesser accurate calculus. In the experiment number 2, as the table shows, the repetition of the steps gave similar results to each micropipette. Even in the P200 assay was reported an efficiency of 100%, while the P1000 presented higher levels of errors. It was also calculated an average and standard deviation.
In conclusion, the correct manipulation of the genetic engineering laboratory materials and equipment is mandatory in order to obtain accurate measurements and results. However, errors should always be considered as they cannot be eliminated.